Hello, folks. How's everybody? This is Rational Science. And I was laughing a little bit. Someone put a comment here. Gravity is an electrical effect. And he goes on, stating how electricity does gravity. I guess we have a thunderbolter here today. And he says, I don't know why this is so hard to comprehend. Yeah, tell me about it. Anyways, I was sick for about 10 days. I'm still a little congested. I haven't gotten over it completely. And I put some nose drops a little while ago so I could speak a little better because I'm still have a little bit of congestion. Anyways, I'm going to skip the extinction segment today because apparently I can't take a break. I took a break and got twice as many comments and questions to answer. And so I'm going to spend a little bit of time on that because there are a lot of misunderstandings, especially people who think they can dabble in physics, but they haven't taken, the basics. They don't understand the basics. And they use a lot of the words that mathematical physics has put into their heads, like field, electricity, like this, plasma, ether. We're going to be dealing with that a little bit today. Mass, energy, field, time, charge. All those words have nothing to do with physics. We wipe them off the map. They have nothing at all to do with physics. So anyone using those words has not taken his first introductory course, his kindergarten course in physics. Okay, here's one famous etherist, 18th century. And this is what he had to say about ether and gravity, how the ether causes gravity, or what the mechanism is. And his name is Euler. That's after he took some ether and it went to his head. And no, that's not what he looks like, but I think that's what happened to him. He just took a lot of ether and it went to the, to the ceiling. Anyways, this is Euler here, okay? And he says the following. He says, those who attribute gravity to an attractive force of the earth base their opinion mainly on the fact that otherwise no origin could be displayed for this force. But since they proved, I like that, they always prove, right? That all bodies are surrounded with ether and are pressed by the elastic force of the latter, we do not need to search elsewhere the origin of gravity. So you can see that he's already figured it out. Only if the pressure of the ether would be everywhere the same, which assignment is indistinguishable from that of its equilibrium, would the bodies be equally pressed from every side and thus would not be induced in any motion. But if we assume that the ether around the earth is not in equilibrium and that instead its pressure becomes smaller as one comes closer to the earth, then any given body must experience a stronger pressure downwards on its superior surface than it does upwards on its inferior surface. It follows that the downwards pressure will have the advantage and hence the body will really be pushed downwards, which effect we call gravity. And the downward pushing force, the weight of the body. And this is good old Euler. He was the #1 mathematician of the 18th century. Some of them consider him the best, I guess, mathematician of all time, or one of the top honchos there. And this is what this fellow was proposing. He was proposing ether. And here, let me illustrate that for you, what he's just said. This is what he was suggesting. He's saying, look, here you have the earth, and you have all this ether. You can think of it as a fluid made of particles. Some say it's made of a single piece, that it's not made of parts. You have all different versions out there because no one's ever defined or identified the ether. Okay, they've never started by saying, look, this is the ether, and with this thing, I'm going to be doing my gravity, my electricity, my whatever, right? No, they just went in there and said, well, the ether, that fluid that's over there, covers the entire universe, and they start using it, and they say, look, all these particles are pushing you towards the earth. And so they have this push gravity, right? Based on particles or whatever they think the ether is. I put particles here because no one tells me what the ether is, so I have to tell them what the ether is, and they can challenge it. And so what's the problem? The problem is that the moon also has, this situation where all the particles are going toward the center of the moon. And so how does the Earth attract the moon if all the particles over here are going towards the Earth and all the particles over there are going towards the moon? So that's what you got to answer. And so Euler apparently, with all his math, he was a great mathematician, came up with the most ridiculous explanation for gravity that anybody can come up with. And that's the situation today. We have all these mathematicians. They know their numbers and their variables, by heart, like the palm of their hands. And they can't tell you how a spoon falls to the floor. That's the situation. That's the state of physics today. Okay, and then we have another etherist, and I'm sorry to see him go. He says he quit my channel. He unsubscribed. How dare he? How dare he unsubscribe from my channel? I forbid it. And this is what he says, okay? He says, I won't even bother watching the video, the one I put last time. Unsubscribing anyway. Yeah, and so what was the issue? Well, the issue was that he ran away, with his tail between his legs. So what was this etherist saying? Well, apparently he couldn't bear to watch. That's why he just quit. But the interesting thing is that he deleted all his comments. Okay? And the only thing I'd like to mention to him, if he allows it, right, is that he forgot a couple of comments in this video that I've got by the name of, titled, of etherists and black holders. And he's got a couple comments still in there, so he hasn't gone completely away, but I'm just reminding him so that he has a chance, to delete further comments. He just forgot a couple. Okay. So yeah, that's what they do. They and that's one of the reasons I don't answer comments anymore in on YouTube directly. I address them here. So what I do is I collect all these comments, these feedback, questions, whatever, and then I can analyze them and give them an answer here. And so they have an incentive to come and see me the next time. That's one issue. But the other one is, if they're going to delete their comments or they're wiped out because YouTube cancels their account or whatever, well, then what you see later on is that you're talking to the wind because you see a bunch of answers and you don't know what the questions are, or vice versa. So I don't do that anymore. If you go to my early videos, I used to answer a lot of questions, and today you go there and it's just blanks. People drifted away. Okay, so this is what this fellow says. He says he deleted his comments. Then he says he didn't know what the ether is. And this is how he really started. He says someone already proposed the only rational mechanism. Let me get this out. For gravity and electromagnetism using the universal continuous fluid medium, not made of any discrete constituents. So he's got this continuous medium made of a single piece. It's flexible. It's fluid, right? That's what he thinks the ether is. And it's not made of discrete constituents. Okay, he spelled it wrong there. But the point here is, I think everybody understands this. What he's saying is this fluid fills all of space, right? Completely, meaning it's got to be finite, because hopefully space is finite if he's going to say that ether is a physical object. Physical objects are not infinite. There's no object that is infinite. All objects are finite. And so he should be able to illustrate it for us, right? So he explains it. He says some kind of fluid that is not made of discrete constituents, and he's going to use this, to do his physics. Okay, that's how he starts, and he talks about proving and disproving the ether. We don't care about that. We don't prove or disprove anything in physics. We need to know what your, or understand what your ether is so we can follow your presentation. You have to tell us what the ether is to you. I don't care what the real ether is, okay? I want to make sure that's clear. We don't care what the real ether is. But when you come and give your presentation, your dissertation, you had better tell the crowd what you have in your mind, in your mind. You have to tell them, this is what I say the ether is. Then we can follow your presentation. But to say, look, everybody's got it wrong except me, and then you don't tell me what the ether is to you, we can't follow your presentation. That's how simple it is. Okay, so I went into kindergarten physics and I said, welcome to physics kindergarten. What is the ether? Okay, I want them to tell me what the ether is, right? And so I asked him to point to the ether, and he had this. He started saying the ether is some kind of fluid, flowing fluid, or fluid that is flowing. He just kept talking about flu. We never understand what these people are saying, what they're talking about, what they mean. When we don't know if it's an object or a concept. Are they talking about an abstract concept? Are they talking about a real thing? Are they going to use it as a baseball bat? I mean, I don't know. They have to tell us. And so I just wanted him to point to the ether. And I guess he couldn't do that because this is what he said. He said here, first, this is what the reason I asked you is you got all these versions of the ether out there. This is the one that you'll find if you do a Google search in images. You'll find all these versions of the ether. You find all these arrows, dotted or dashed arrows. I guess they're referring to particles sweeping across the solar system. That's what it looks like, okay? And that's what people have in mind when they're talking about the ether. They think of it as some kind of fluid. Fluids are all made of particles. These people say it's a fluid. Some of them say that it's a fluid made of a single piece, that it's continuous. It's not made of constituents. Okay, fine. That's great. But then draw it. Illustrate what you're saying. I want to see the shape of the ether. See, what these people want to do is they want to say, look, the ether covers all of space. It's everywhere, right? I can't see it. I can touch it. It covers all of space. Okay, no problem. But now they want to use a chunk of that, and they say, look, the ether over here does this, here on Earth or in the solar system, whatever. You can't do that. The ether, the whole shebang. You got to move the whole elephant. You can't say, I'm going to take a piece of the elephant and do this with it. No. Ether is the whole thing. Either you use a little thing or you use a big thing. Either ether is that little thing that is a portion of something else, and you're just going to talk about that, call it ether X, give it a different name, right? You can use ether X for whatever you want, but that's the ether. And again, you have to draw it before you do anything. But these people say it's the whole shebang. It's the ether covers the entire universe. It's a blob. It's I don't know, fluid. Flowing fluid, or maybe it's a static fluid. I don't care. It doesn't really matter. And then they want to use a piece of it. No, you can't do that. You've already contradicted yourself. So this is where the problem lies. Okay. And so he says the following. He says, "You want me to draw you the ether? Yeah, I want you to draw the ether, or point to a site where the ether is illustrated. Or something. I mean, if you're going to treat ether as a physical object, point to a site where I can see the ether. I want to know what you're talking about." He says, I don't know what the ether looks like. Oh my God. So he's going to talk about how the universe works. He's going to tell us everything that he knows. And the first thing he says, I don't know what the ether looks like. He says, it's all supposed to be invisible and tangible, remember? Okay? Not good at drawing stuff. And that's all very childish, Bill. He says, I'm being childish because I'm requesting your word salad from him, For him, all these words just go through one ear and come out the other. It's got nothing to stop it in between. Okay? Okay, does he stop there? No, he's going to tell us how light works because he knows exactly how light works. And here it is. He goes in there and he says, as for light particles, light does somewhat behave as particles. Okay, behaves somewhat like particles. Okay, whatever that means. But I don't believe they are the kind of particles many believe in. Good. I want you to show me your particles. They are not spherical beads. Okay, so they're not like everybody else thinks of beads. What are your light particles? What do they look like? Well, I mean, show me one of these particles that you have in the back of your mind. And he doesn't. He just goes, the particles don't have any specific structure or size. That's all he said about him. He didn't tell us what it was. He didn't illustrate. He didn't point to a website saying this is what a particle looks like, the particle that I'm talking about, okay? Fine. He didn't do that. And he said, you won't find a more rational explanation for light on YouTube. And there you can see light particles explain rectilinear propagation. That's what he's going to argue. And no, the first thing anybody has to accept is that you cannot simulate either light or gravity with particles, with discrete particles. Okay. In fact, quantum mechanics gave up on that a long time ago, about 100 years ago. Before that, they had corpuscles. Newton's corpuscles, the corpuscles they were thinking about ever since the 17th century, and they gave up on that. We cannot simulate it with corpuscles in great measure because a stream of corpuscles cannot, under any circumstance, travel in a straight line, travel rectilinearly. So that already eliminates the corpuscle. We'll call it a corpuscle instead of a particle. Okay, so what does this fellow explain with his corpuscles, with his undefined corpuscles? And here it is. He says, light particles explain rectilinear propagation and reflection. The more you get near the spot where the incident ray's reflected angle becomes zero, the reflected rays are now directed towards the screen. But due to the surface being curved, what we observed is that the rays reflected many different angles according to the law of reflection, whatever that is, okay? Each reflected ray, talks about rays, talks about light. He's not talking about whether it's particles or whatever, is making a new dot on the screen. At 0 degrees, most of the light is pointing straight and making the central maxima. Okay, how does it do it? It says, this is his whole explanation. Some rays are also deflected or diffracted inwards. In other words, you see the red dotted line there, the red dotted arrow. He's saying that it turns the corner. Turns the corner, why? Because we have a rounded object, which in this case is a needle seen from above. Okay, it's a needle, so you're pointing the laser or the light at the needle, and the edges of the needle, he says, allow the particles to go inwards towards the red spot. And that's magic. That's never happened in our universe, maybe in his universe, I don't know. And so he says deflections explain the bending of light around corners. Yeah, we have a little bit of problem with his explanation, okay, of how he does his physics. What's the issue? Well, here's the issue. I'm trying to illustrate it here for you, okay? You throw a ball against a tree, okay, and he says it goes inwards. We know that these particles, they can go towards outside, like this one here coming up. It bounces, goes outwards. That we all experience. But this one where it goes inwards, that's what we want him to explain. And he says it's just the law of reflection. I guess he's a very reflexive guy, okay? And so when I press him on that, he says, I already explained why light appears to bend around corners. I won't bother once more, okay? And again, he repeats that light reflects off the sphere near and from the edges of the circumference, which is curved. So he says it reflects, but he thinks reflection goes inwards. Reflection always goes outwards, and I challenge anyone to throw a ball against the edge of a tree and we find out that the ball will bounce outwards, never inwards. Okay, so how he gets this reflection of particles, right, to go inwards, that's where the mystery is. That's black magic. And then he just continues saying the same thing, okay? And just so you see that I'm not putting words in his mouth, okay? Here's his version. This is from his website, his YouTube site. And I put this up here so that you can see how he explained. Essentially, he just said, it is so. That's all he said, okay? You'll see how he explained the passage of light, okay? So here it goes.
Pay attention to the red arrows. The more you get near, the spot where the incident ray's reflected angle reaches 180 degrees, the reflected rays are now directed towards the screen. But due to the surface being curved, what we observe is that the rays reflect at many different angles according to the law of reflection. Each reflected ray is making a new dot on the screen. At 180 degrees, most of the light is pointing straight and making that central maxima. However, notice how some rays are also deflected inward, contributing to the central maxima. The law of reflection does not account for surface imperfections at the microscale, causing diffuse reflection. But those imperfections could explain the apparent bending of light around corners.
Okay, so that's his explanation of how light travels and how light turns corners. He's saying it doesn't turn corners, irrelevant. The point is that he is turning the corner with his light. He's turning it. He's saying it's through reflection. We don't care what reflection means. He should talk in straightforward physics language. He should tell us how a ball goes around, which is curving. That's what he's saying. He says light curves, but he's just saying it's done through reflection. No, what he's got to show is how a ball goes around a needle. That's all he's got to show us. And I'll illustrate that as well. Here it is. This is the standard version of the slit experiment. Okay, and the question is, you can see that the balls that the source is sending is hitting the edge of the slit there, the frame, you could say, right? And bouncing inwards. We all understand that because we all, threw a ball against the wall and found it bounce back. So that's not an issue. This is the issue. The issue is if we're going to replace now that slit with a needle, okay, we're going to put a needle in there in the center, okay, and here it is, okay. And so if you put a needle, now you still have the fringes on the screen, but the question is now you don't have the slit there. What you have is this round needle in the center, and the question is how do the photons or particles or whatever turn the corner? They go straight ahead, and that's a whole issue. The whole issue is that you can't explain this with particles. Particles don't turn corners unless you can explain the mechanism, how it does that. Okay, and to say it does, it's like quantum. Quantum also likes to tell you that the particles can be at any place at any point in time because it's like they're everywhere, right? And all at once and whatever. Well, that doesn't explain anything because if that's the case, then it would be random. Okay, you would not have the particles producing the interference pattern that quantum champions. That is the explanation today, that there's an interference, both constructive and destructive interference, and that makes the fringes. But if the quantum particle is allowed to be anywhere and everywhere at any point in time, then there shouldn't be any coherence there. We shouldn't get these fixed fringes, which is what we actually see. Okay, so here's the wave version, and that quantum also offers. And the only thing I want to mention here is when they do the slit experiment with waves, they use water waves as the simulator. And that's a problem because light is not alleged to be both longitudinal and transverse. It's alleged to be transverse. And what they do, they have this longitudinal component, which you see there illustrated, which is that the particle goes backward. Okay, particle goes backward, and because you get this rarefaction, compression and rarefaction going back and forth like with air, and so the particle goes backwards. That doesn't happen, or that's not proposed that it happens with light. Okay, light is only transverse; it's not longitudinal, and they use the longitudinal component of the water waves, right, to simulate light, to simulate how the waves spread out after going through the slit and interfere with each other. And that's cheating, okay, because they never proposed that light is a longitudinal wave. Okay, it's just a transverse wave. There's no longitudinal component, which is what causes, that interference pattern right after the slits. Okay, so the issue there, part of the issue was ether, What is it? And the other issue was light. Does light turn corners? Okay, and apparently this fellow said it does turn corners, but it don't. It turns corners because it reflects, not because it swerves. That's essentially what he's saying. But he's doing it with particles, so he is, whether he knows it or not, talking about swerving. He's saying that the ball rolls around, so to speak, the needle, and goes behind, the area that is blocked by the needle and creates the Poisson spot. Okay, so let's continue with some people who also ask questions with regard to whether light curves or not, whether light, and the question again there is whether it swerves or deflects or curves. Are we talking about a ray a curved ray, a bent banana? Is that what we're talking about? Or are we talking about a little ball that is, curving or following a curvilinear path through space? Those are not the same, not equivalent. And that's more or less the problem here. A fellow says the following. He says, how does light turn a corner? And that's the wrong question. That's the wrong question, okay? Because he's using the word light. He can't use the word light. He can't use the word ray. He's got to tell us what he's talking about. Is he talking about particles, or is he talking about waves, or some other proposal that he's got, okay? And so if you have a stream of particles, you cannot turn a corner, okay? So if he's going to simulate it with a stream of particles, he would have to tell us how he envisions those particles turning a corner. And a wave is the same thing. How does a wave turn a corner? That's all he's got to say, okay? And here's a picture that I've got, okay? Let me get this one out, of light coming between the door and the wall, okay? And you have light coming through there. And apparently light is curving around. You can see light, at least from the left side, is turning left as soon as it leaves the door or comes through the door. And the light from the right is curving as it comes through the wall, okay? But obviously we can do this with straight lines. There I've put the straight lines for you, okay? You can see the red lines there that I put. And you can see that this can be done all with straight lines. In fact, light always travels straight, rectilinearly, in other words, right? If we're going to talk about travel, there's really no real travel under the rope model. It's just torsion, in situ torsion. So there's no traveling. But if we're going to talk about travel, yeah, we can say that light travels straight. The signal travels along the rope. So if the rope is taut, it had better be straight. In other words, it should be traveling rectilinearly, propagating rectilinearly along the rope, because the rope is taut and it's the torsion of the rope. So it's very straightforward, right? And yeah, here you have it with the rope. Here you can see the atoms there. I put some green atoms and just a few of them. And you can see that if the red lines are the ropes, right? And I didn't put all the atoms, all the ropes, obviously. But you can see that from atom to atom, you have a straight line, and that's a rope that's connecting any two atoms. So yeah, we can do it with particles and with the rope, no problem. The particles are the atoms. So any atom there that you can see in that room, right, will be connected to all other atoms by straight ropes, taut ropes. That's really the correct word. They're taut. They're stretched as tight as possible. And here you can see the model, okay? We have the atom pumping back and forth. They torque the rope, and by torquing the rope, you can see that the torsion really doesn't travel anywhere. What it is, it just gives a thump at the both ends at the same time. So you could say it travels in both directions, opposite directions simultaneously, okay? Because both atoms receive a bump right at the surface of the atom. So that's our atom, and so yeah, we can explain straightness. We can explain why light always travels straight. Okay? And here is another piece of evidence that you can ponder, and this is evidence. There is an explanation here. The explanation is the following. Here you see the Earth, And what we have is a laser that is a big monster laser that's pointed from the Earth to the retroreflectors on the moon. And you can see why light always travels straight, because whether the moon or the Earth move is irrelevant. All the atoms of the moon are tightly bound to every atom on Earth, so the ropes are all pulled as tight as they can be, and the torsion travels along a straight rope. So the moon can go anywhere it wants now, because the light is just going to travel along the rope. And at the same time, there you see the cause of gravity. As the moon approaches the Earth, you will see that the ropes fan out. Okay, so we have both. We have like a grand unified theory here. We have both light and gravity in a single mechanism. But the point here is that the ropes are stretched as tight as possible, and the torsions travel along straight ropes. Okay, and that's why you receive the light in your eye, because every atom in the room is connected to your eye through the electromagnetic ropes. That's how simple it is. Okay? Okay, why can't we do it with particles? Well, here's the simulation for particles. This is why you cannot do it with particles, okay? You have this is the sun, okay? And the sun is made out of atoms. Every atom in the sun, well, first of all, the sun is twirling, right? It's spinning, right? But then every atom in the sun is also spinning and moving around and doing whatever. And so any photon, any particle, any discrete entity that you want to mention that comes out of every atom that makes up the sun has no chance. A whole series of them coming out of one atom has no chance of traveling in a straight line. It looks more like a sprinkler system. It just goes around and around and around, sprinkling all these particles in curves, never in a straight line. And that's where the particle hypothesis dies completely. Okay, and then we have here the wave version, the transverse wave. This is what a transverse wave looks like. Okay, this is the one proposed by quantum mechanics. It's the one that's been analyzed for at least 2 centuries now. Okay, they had this transverse waves. Okay, and so what are we staring at? Well, we can't use this as a mediator for light because it's made out of vectors. They call it field, so we have fields and vectors, both of which are mathematical concepts. You cannot say that a mathematical concept is a mediator of light. And so the wave, the transverse wave, dies right there and then. In fact, here you see a comparison of what happened. They confused the rope with a wave, with a transverse wave. So they were always talking about these transverse waves when what they were really looking at is the torsion, in situ torsion, of a rope. And you can see why they got confused, because they are structurally very similar, okay? The only difference is that the wave cannot explain c equals frequency times wavelength. C, the velocity of light, is a constant, and it's 300,000 kilometers per second. And when you raise the frequency, you have to lower the lambda, the wavelength, and vice versa. And with a rope, you can explain it very easily. If you increase the number of links for the same amount of rope, you can do this at home, you will see that the links will become shorter, and vice versa. When the links are longer, well, you have fewer links. Very simple. That's the equation of a rope, what you see in there. C equals frequency times wavelength. So you can see why they got confused, and they thought of a rope as a transverse wave, and to this day. Okay, and what is a wave made of? Well, sometimes they say it's made out of particles, because what is a wave made of if not vectors and fields? Well, here's a wave made out of particles. And no problem, we can accept that. The only problem is what makes each particle go up or down. I mean, are they tied together? Are they bound one particle to the other? So again, we have a problem here, because all these people just make assumptions, but they never illustrate what they're talking about. And because they cannot illustrate or don't illustrate, it's that they can never explain, because we don't have the images that we need to understand the presentation. Okay, here we have another fellow, and he says he does mereology. Okay, mereology is a religion invented by first the mathematicians. They passed it on to the philosophers on the other side of campus, and they created a cottage industry of mereology. what is it? Parts of whole and temporal parts. You know, they divide things up and they say what something is made of. And this fellow has this in the back of his mind, I guess, and he says, I can describe a singular part of a medium as having shape, location. Yet you deny the existence of a medium composed of many such objects. Okay? I don't deny the issue is something else, so I don't know where he got that. I would say that a medium is a composite object. That's where we have a problem. No, a medium is not a composite object. That's an irrational definition, okay? And that's an irrational notion. As in an object composed of many smaller objects, that's irrational. How is that not rational description? I'll tell you in a second. There are many examples of composite objects. Yeah, I'm sure there are. If your rational model has no way to recognize composite objects or composite motions or composite processes, then it can't possibly be describing nature. Okay, so what's the issue? Well, the issue is we have to take this poor fellow to kindergarten physics. See, all these people, they want to do college physics, you know, high-level physics. They have never gone through kindergarten physics. They've never gone to first grade. And so let's start at kindergarten physics. I hope some of you who've been around, I hope you don't get bored too much, okay? But I got to go through this stuff because you have people like him that don't understand basic stuff, kindergarten stuff, something that a 10-year-old would be able to tell them. So let's start there, okay? And here it is. Welcome to kindergarten physics, okay? Today, children will learn necessary word salad to do physics. In physics, all objects are made of a single piece. Let's repeat that because I don't think he understood that. All objects are made of a single piece. They're all continuous, made of a single piece. Okay, an object is that which has shape, and there you see some synonyms, including the word he was raising question of, medium. A medium is the same thing as an object, a thing, and it's all made of a single piece. Okay, and so he might say, well, that's your opinion, Bill. Okay, let's do a little more than an opinion. Let's see if we can educate them. Maybe we can educate someone today, okay? Here, Klingon comes to Earth, and good old Uncle Sam stands next to him. And he says, I don't understand your language, Sam. What is that? He says, table. And so the question is a table made out of legs, a board, atoms, molecules? Absolutely not. Table is made out of a single piece. Okay, we got that? Table, the word table, single piece. It's that whole thing. Okay? It's not made out of parts and not made out of, you don't say table and say, well, but it's got legs, it's got a board, I can sit on it, I can put a dish on it. Nah. Table is that which I pointed to. And that thing, at that moment, is made out of a single piece. That's how you present objects in physics. Okay, let's try something a little more difficult. Let's try the word chair. Chair is also made out of a single piece. You say, hold it, Bill. It's got some boards there. It's got some legs. It's got a seat. Sorry, the word chair refers to that whole thing. So when I say chair, I'm referring to that whole thing. That's made out of a single piece. Not made out of atoms, not made out of molecules, not made out of anything. Okay? It's made of a single piece. Continuous, right? And here we have the word tree. I hope you're learning some language today, you know, what things are, okay? Tree, and you point to it. No, but it's got leaves and branches and roots. No, bark, no. No, it's made of a single piece. The word tree refers to that thing that's made out of a single piece. Okay, so where does the problem come in? Well, these people say, well, what about mediums? You know, media. And here you have one, and Sam points and says, ocean. Says, oh, but an ocean is made out of water and all these drops and H2O and... No. An ocean is not made out of fish, out of boots, out of dead people. None of that. No. Ocean is made of a single piece. Now, in this case, maybe I forgot to put the edges to the ocean. Okay, here, let's put some edges there. Okay. But ocean is made out of a single piece. That's what I'm pointing to there, or what Sam is pointing to there. That's an ocean. Okay? The whole thing is an ocean. Ocean refers to the whole shebang. Doesn't refer to a little piece of water. And this is what these people don't understand. They start saying, oh, the ether, it's a blob that covers the entire universe. I'm going to take a little piece of it and show you, you know, how the ether does electricity or gravity or whatever. Now, you can't do that because you defined or you pointed to this blob that is the whole universe, and it's made out of a single piece. So you cannot take a chunk of that and say, I'm going to do something with this little piece of ether. No way. No way. You're contradicting yourself already. And that's what these people want to do. They say, it's made out of parts so that I can take little pieces of it out. That's why we ask them to illustrate, okay? And then we have here the air. Okay, another big problem for a lot of people. People get so confused with air. You know, it's a gas, and it's color-coded there with light blue, I guess, unless you're colorblind. Okay, is air made out of particles? Is air made out of molecules and atoms? Absolutely not. Air is that whole shebang that you see there, the whole bluish, light blue thing that you see there. That's air. Okay, and here's air around the Earth, and that's what air looks like. You know, if you color code air, that's more or less what you would see. You would see, you know, all this. In 2 dimensions would be a ring, and in 3 dimensions it would be, you know, like a shell or, you know, covering of the Earth. In fact, let's remove the Earth from there so that you can see the air better without the Earth. There you see it. That's air. It looks like a shell, maybe a ring if it's 2D, you know. That's air. Air looks like that. And one of the big problems that a lot of these people have is they say, you know, they're under the impression that you need pressure. You know, that when you introduce particles, they tend to move to the area of lower density. And so they say you need some kind of wall to contain all that stuff, you know, because otherwise the particles will fly away to a region of lower density. Well, the Earth is not covered by any walls. God did not make a sheath around the Earth, around the air. The air can leave if it wants to. There's nothing blocking the exit of air from the Earth. And so the question is, you know, when you see the black stuff out there on the outside, that's lower density. That's space. That's vacuum. Almost, you know, perfect vacuum, but certainly much less dense than the air that's covering the Earth. So why doesn't the air leave and go to areas of lower density if there's no, you know, container, no sheath covering the Earth? God didn't make one, you know. The air is free to go, and it doesn't go. It stays there. And so, yeah, these people are wrong. These people don't understand basic physics, and they start saying, oh, the air would go to a region of lower density. And here you can see it doesn't. It stays there. And so we have to show why it stays there. And yeah, it's got to do with gravity, okay? And but let's continue here. And here we have the astronaut. And he's going to take a balloon full of air. He's going to pop it in the middle of nowhere. You know, that's the second frame there. And he pops it. And what comes out is air. We color-coded it white so that you could see it. And that blob there, that's made out of a single piece. Air is the whole thing. Air is not made of molecules. It's not made of particles. It's not made of atoms. Air is the whole thing. The whole ball of gas, the blob of gas, that's air. When you say air, you point to the whole thing. You don't start breaking it up in pieces and say, well, this piece of air and that piece of air. No, air is the whole thing. And these people have a lot of trouble understanding these basic, you know, kindergarten stuff. And here, why not? We point to a rope. So, a rope is made out of 2 strands. No. Rope is what I pointed to. The whole thing is made out of a single piece. Oh, but it's got different colors. Yeah, I'm sorry. I should have colored them with a single piece. Rope is what you see there, the whole thing. It's not made of parts. Okay? And so, in physics, every object that is presented is made of a single piece. If the colors distract you, you know, just try to get a little Daltonism and, you know, forget about the colors. Rope is 2 twined threads made of a single piece. That's what I pointed to. That's a rope. And so this guy's, you know, they want to introduce notions which they never thought about, obviously. And they say, oh, medium, it's made out of particles, and we take a chunk here and a chunk there, and we do whatever we want with it. No. Ocean, air, rope, made of a single piece, always. Okay, when you present it in physics. Okay, then you can move the whole thing any way you want. That's what you got to do with ether. Ether is made out of a single piece. Okay, so whatever ether is, just draw it and then do whatever you want with it. And of course they can't, because they want the ether to be a concept blob that occupies all of space, meaning up to infinity, and it covers everything, and at the same time, it's made out of a single piece. It's continuous. It's not made of parts, and at the same time, they want to take a chunk of it and say, "Look what the ether did over here." No, you can't do that. You're cheating. Okay? You already contradicted yourself. Okay, one fellow says the mechanism makes no sense and is inconsistent with the inverse square law. He's talking about my video where I showed that objects approach each other, and as they do, as the distance decreases, and there we have Newton's gravitational equation, or part of it. As they do, the ropes fan out. And so the closer they get, the faster they come to each other, acceleration of gravity. Why? Because the ropes fan out. There's more and more independent ropes, okay, simply as a function of distance. And these people they can't understand something as simple as that. And so he says it should be inconsistent with tension dropping off with the square of a distance. And what's the problem here? The problem is the word tension. These people don't understand what tension is. They have the irrational notion of mathematics, of the religion of mathematics, of what tension is. And let's just show one more time here. It says when this astronaut hits the ground, showed the astronaut coming towards the Earth, the ropes fanning out as he approaches the Earth, right? Isn't there even more ropes around him? I don't know what he's talking about. I mean, is he being hung by a rope? I mean, I don't know what you mean around him. Are they stuck to every one of his atoms? That's so. There are not more ropes. What we have is more independent ropes. They're not on the same axis. As the guy approaches the Earth, the ropes fan out. What part don't you understand about this simple baby kindergarten stuff? It just boggles the mind. The way you depict the ropes implies to me that there would be a stronger tension further away than close by. And again, he doesn't understand what tension is. We need to explain tension, not the mathematical tension he learned at the monastery. We're talking about physical tension, which is a totally different thing than what the mathematicians have out there, okay? And that's where he gets confused because he's thinking of mathematical tension, not about physical tension, which is the opposite of what is required by Newton's gravity equation, which follows an inverse square law, and he just goes on there and on and on. Okay, so he's talking about tension. The tension is always the same on every rope in the universe. It's dictated by the velocity of light, c, 300,000 kilometers per second, which is a constant. Now, light always travels at the same speed. Why? Because it's the tension on the rope, which is the torsion that we have on a tense rope. And so the rope never becomes flexible, except under certain circumstances, but normally they don't between atoms, right? And what happens is that you have torsion of that rope and you have light traveling at c because the tension on the rope is always the same. All you change is the frequency versus the wavelength, meaning the frequency number of links versus how long the links are. Very simple stuff. Really very simple stuff. This is kindergarten stuff. The universe is a very simple place. The mathematicians have made it a complicated place because they started taking measurements, doing equations, say, oh, I don't understand all that stuff. Of course you don't. But Mother Nature never went to school. She just deals with rocks, planets, particles, atoms. She just moves one atom at a time from one place to another. So does Father Universe. They don't know anything about math. These relations that humans created. They know nothing, and they never went to school. Okay, so another fellow along the same lines says, I understand the ropes to be under some level of stress, and said stress might have to be attached to a star rather than just other earthbound atoms. Yeah, again, these people are talking about tension and stress, and so let's find out what tension and stress are in physics, because these people don't understand that. First, let me illustrate this here. Just so you know, the mechanism for gravity is right there. You can see it on the left. As the cylinder approaches the cube, the ropes fan out. So originally, they were all these atoms were on the same axis. So it's like a single rope tugging, you could say number 1 to number 6. It's like 2, 3, and 4 do not exist because they're on the same axis. So number 1 is tugging from number 6. But what happens? As the cylinder approaches the cube, because of distance, because only the change in distance, we see more ropes. Each one that was on the same axis before, now they're all on different axes. And what happens is now you have greater tug because every rope is acting independently, what we call an effective rope. And there on the right, you see what happens at far distances, far away distances. What you have is all the ropes come together and act as a single coaxial, so gravity is very weak. And as it approaches, the cylinder approaches the cube, what you see is the ropes fan out, and you have all ropes acting independently. There you have the acceleration of gravity in a mechanism. Okay, something mathematical physics has never been able to do. Okay, and so what's the issue? Okay, so here, let's go with what this word tension means, stress, Here's from the Stack Exchange. Tension is the stretching of the rope at molecular level. No, that's not what tension is. What these people are saying is that tension is a pull, two pulls. In other words, a force. And the greater the tension, meaning the greater you stretch something, the atoms are all, or the molecules, right? They're all tugging and trying to stretch with respect to each other. That's not tension. That's called pull. Pull is a force. Tension is not a force. Not in physics. Tension is when we reach a stalemate, when no one wins the tug of war. Okay? When everything is stretched to the limit. Like the rope, because see, the thread that makes up the rope is made of a single piece. It doesn't stretch. We don't create matter by stretching the thread. That doesn't happen on the rope model. There's only so much matter in the universe. It's a finite amount of matter because there's a single thread that makes up all the atoms which are connected to each other by ropes, all of it made by the same thread. Okay? And so here we have again the Wikipedia version of tension. It says, tension is described as the pulling force. Yeah, they're talking about pull. They're talking about a force. They're not talking about tension. But they put numbers to these things and they say, oh, the tension is so much because one's pulling from here and the other one's pulling from over there. So they say, what's the tension? How much tension is there? And they talk about quantities of tension. That's where the problem is. No, tension, that's pull. That's called pull. One's pulling here, one's pulling there. Even if the elephant stands still and you're pulling on it, the elephant is pulling on you because he's this great inertia, this block that's preventing you from taking the elephant with you. Okay, so the elephant is pulling on you no matter what. It's called pull. It's not called tension. Tension is something else. And here's another definition just in case. Tension is a force, and they go through all this stuff showing that you need an elongated object to produce tension because it's a pull force. It's not tension what they've been talking about for the last 400 years. They're talking about pull, a force. And here's an example, okay? It says, there are two people, A and B, in space with a taut rope, no tension currently in between them. If only A is pulling and B is not, then the tension is equal to the force A exerts. If B is also pulling, both of them pull from either side with a force of 100 newtons. Then the rope at the end of B will pull B with a force of 100 newton, and by Newton's third law, the rope will experience a pull of 100 newton. But B is also pulling his end of the rope with 100 newtons. So I guess we have 200 newtons of force, not of tension, of force. So whenever you pull, if you still haven't finished stretching, whatever you're stretching, then we have pull. We don't have tension. So far we have no tension. Tension is a tug of war where no one wins the game. There's a tie game, or better yet, I like to say it in different ways, and you better sit down and listen to this. Tension is a stick made of a single piece between two objects. Let me repeat that. Tension, yes, stress is when you put a piece, a stick made out of a single piece between two objects, a dumbbell, in other words. And I think these guys are the dumbbells. A dumbbell is tension. That's what it is in physics. Tension means nobody wins the tug of war. If someone is winning the tug of war, you have pull, not tension. Okay, so along the same lines, one fellow says, what happens to atoms at the edge of the universe when atoms are destroyed in a nuclear explosion? He's talking about the thread or rope version of the atom, right? Do threads break in such circumstances? And so here are the answers very quickly. Really, atoms are indestructible, okay? It's made out of a single piece of thread throughout the universe, so every atom is made of that same thread, and it's a single closed loop thread, so that's all there is in the universe. If we untangled every atom, every rope in the universe, we would end up with a single thread. Enormously big, very thin, and made of a single piece, malleable, etc. Those are the characteristics. Naked atoms release neutrons and decay swiftly to smaller non-radioactive atoms. Yeah, but, in other words, when you have nuked atoms, when you have a nuke, an explosion, all you have is decay of the atoms. So if you have uranium, it'll decay, I don't know, to radon or to even lower to lead, which is non-radioactive. So that's all you have. So there is no disintegration of the ultimate atom, which is the hydrogen atom. That's the only real atom that exists out there. All the others are composites of the hydrogen atom. More hydrogen atoms together with neutrons, they make up bigger atoms. That's all we have today. But if you break it all apart, you end up finally with neutrons on the one hand and hydrogen atoms on the other. That's all there is, ultimately. Single thread is made of a single piece, okay? And again, it underlies all atoms that interconnect them, right? The single thread. And single thread is not made of parts. It's not made of discrete segments or little dots or anything, points. It's made of a single piece, okay? It doesn't stretch because it's made out of a single piece, okay? Single thread cannot break or be cut, okay? You cannot break it. And so, yeah, the single thread is what makes up everything in the universe. That's our hypothesis, called an assumption. We make an assumption so that you can understand the theories founded upon that assumption. Okay, here we have a fellow, he says, the fundamental single thread, trillions of times smaller than the Planck length. Yeah, could be even more than trillions, maybe quadrillions. I mean, there's you have the Planck length, and I just drew more or less, right? Obviously, Planck length is very small, but the thread is maybe thinner than the Planck length. It's no problem in physics. That's just a question of smallness. So we have no problem with how big, how fat things are. That's a concern for mathematicians. Okay, the fellow says, gravity counteracts the depressurization. And what is he talking about? He's saying, again, what I said earlier, that you have air around the Earth. Why does it leave? Why does it go to a region of lower density, which is space? Is there a sheath or a container, holding the air in around the Earth? And the answer is no. What's holding it in is gravity. But he says gravity is what holds the air in. But that's like saying love counteracts intelligence. You haven't told me what physical entity is holding each atom of air. So forget about using words like gravity and light in very generic terms. Talk about one atom of air that makes up the air and one atom on Earth. Why does this atom not leave? Why does it fall? Okay, you might say, well, it doesn't fall because there's too much density. Fine, forget about that one. Why doesn't it leave? That's the question. What holds that atom there? And hopefully there's a physical mediator between that atom out there and the atom in the Earth. Because if you're saying that there's no mediator because you cannot see or touch something between them, you're going to be doing what is known as action at a distance, which is the scientific term for black magic and witchcraft. You're saying it just happens by remote control. So just be aware of that. Okay, let's continue here. We have, this fellow says, if a black hole is nothing more than a densely packed collection of matter that is hard to see, absolutely not. I have to stop you right there, and I can't deal with the rest of it because you already failed. You failed kindergarten physics. You're not paying attention to what's going on in the world. So let's put some authority. How about Stephen Hawking? I mean, is he an authority or what on this kind of stuff, right? You should know. Here it is. This is what he tells you. Listen carefully, because people are not listening to what people like Stephen Hawking is telling them in their face. They're not listening to Stephen Hawking. So please listen to Stephen Hawking. Don't listen to me. I don't know what I'm talking about, but he probably knows what he's talking about, right? Okay, here it is. So he says the following. He says, Eddington was shocked by the implication, that a black hole, in other words, a star, right, before it becomes a black hole, would collapse to infinite density. Infinite density. I hope you understand what the word infinite or term infinite density means. Okay? And he continues, refused to believe Chandrasekhar's results. Eddington thought it was simply not possible that a star would collapse to a point. What is a point? Zero dimensional. That's what a point is. Euclid told us that, that which has no part, right? Einstein himself wrote a paper in which he claimed that stars would not shrink to zero size. Let me repeat that because you probably didn't hear it. Zero size. We're talking about no volume, no shape, no radius, no diameter, no nothing. There's nothing there. Zero size. Do you understand what zero size means? So this thing that this all says that it's small, this is the notion people have. It's nothing more than a densely packed collection of matter that is hard to see. They're thinking that a black hole singularity, is tiny. And what's the issue? The issue is the mathematicians introduced lousy language that helps them but doesn't help understanding at all. And the word is infinitesimal. And when they say infinitesimal, they have this duality. They mean two things at the same time. Infinitesimally means very, very small, getting smaller, and it also means zero. It means both. That's what the mathematician means by infinitesimally small. Like saying, I didn't go any further. I didn't see how small it got. I just say it just kept getting smaller, smaller, and smaller, and smaller. But it's still small. It's still something there. The onion, you peel the onion, you still find onion in there, no matter what. It's not like it gets smaller and disappears, right? It gets smaller, smaller, and smaller until it gets infinitesimally small, by which later on they treat it as zero, as nothing. And that's where we have a problem, because either the singularity of a black hole is zero size, zero shape, zero volume, or it has some volume, whatever that may be. I don't care. If it has volume, it's a thing. But if it doesn't have volume, it's not a thing. It's called space, empty space, vacuum, nothing. Okay, so let's get the language right. And the question here is that people have missed the language. They allow these people to get away with murder. Okay, they say, oh, infinitesimally small. I understand that. No, you don't, because they're saying zero at the same time they're saying small. And here, just in case, we have another fellow from Cambridge, and he says the following. On solving the equation with particular value rho of central density, you will get a model of a star with mass m, radius r. Plot r as a function of m and show that r, the radius, right, radius, falls to zero. Radius falls to zero. What can that possibly mean? Radius falls to zero when m is equal to the Chandrasekhar mass. If you can do all these, then you have repeated the calculation for which Chandrasekhar won the Nobel Prize. He won the Nobel Prize, Subramanian Chandrasekhar, for proving mathematically that a star collapses to nothing, to zero size, to a singularity. No volume, no diameter, no radius, no shape, no nothing. It's a definition of nothing. In fact, it has no mass either, because it crushes all matter out of existence, and mass is the quantity of matter, or a measure of quantity of matter. There's no matter inside the singularity of a black hole, so it has no mass either. But even if we concede all that, how does non-existent singularity, I'll give them even the density, I'll give them gazillions of tons, no problem. I'll just concede kilograms. how do kilograms move a star? Like they say, the star is rolling around a black hole. There's nothing there. We can't see it, but the star is rolling, so there's got to be a black hole, a lot of mass there. Fine, we'll concede the mass, we'll concede the kilogram. How does the kilogram move the star? I need to see the mechanism, okay? And hopefully it's not, what is it? Kilograms on, number lines, known as spacetime. And we're going to deal with that next. Okay, a couple more issues here. One is touch, a touchy issue. And everybody likes to ask this, they're concerned about touch. If the rope thread here, what is it that prevents some things from melding together and cause other things to become one with each other? Okay, and I don't like to talk about this touchy issue. It's in the book, okay, I was saying. So it's there, it's registered anyways. It's not like I'm going to give you a different version of what's in the book. But it's several pages, okay, and I don't cover this subject first because a lot of these people, they don't understand kindergarten stuff. I'm not going to get into the very touchy issue of touch, okay? It's very complex, and these people can't understand simple stuff, let alone something as complicated as that. I'm just going to give you a couple of scenarios, 3 of them here. One has to do with aggregation. A lot of threads, remember, around the atom, okay, that forms the shell of the atom, our atom, the atom that we have under the rope model, okay? And so you have several windings, many windings, I don't know how many, all I'm saying is there's several windings of thread around the every atom, hydrogen atom. And again, there's only hydrogen atoms, all the rest are just composites of hydrogen atoms. Then you have backscattering. Rutherford, 1919, ended up doing some experiments, and he found out that when he shot some particles against an atom, most of them went through, but some of them bounced back. He said it was like shooting cannonballs at paper tissue and finding the cannonball bounce backwards. And he could not understand that, but he concluded from that the atom was mostly empty space. Well, what was mostly empty space was, the space between his ears. That's what it was, because he reached the conclusion that's irrational. No, an atom is not mostly empty space. It's that their touch is absent from the atom. The only way you can get neutron bombardment to go through is first speed. You have to have speed. The other one is, again, if the neutron goes through one of the sides, it doesn't go exactly in the center, it hits center-wise the atom, then it can go through. But if it hits right in the center, it bounces back. Okay, that's more or less our explanation. That's the quick one. Okay, you got to go to the book to see it in more detail. Okay, but that's in general terms. And then the other one is magnetism. Do the threads touch each other? Yes, they do. I hate to say that here because people say, oh, they touch. No, they don't touch. But for the purposes of magnetism, we have these walls of thread. Walls, aggregation. Okay, you have many walls. Think of paddle wheels of a riverboat, but gazillions of paddles, okay, all around. And they're going like that. And so they repel. And if one goes up and the other one comes down, then they attract. Why? Because there's this very light friction that becomes a monster when you have aggregation. Okay? And that's just in a nutshell, more or less the ideas. There's a lot more. You got to go and look at it in the book. I try to stay away from that subject because, again, people do not understand because they don't know what neutron bombardment is or a lot of those terms that, the experiments that have been run throughout history. They have to get that first underneath their armpits before they can, start asking questions. Okay, and final issue, the fellow says, would you call yourself a materialist? And he goes on with that, saying that I seem to be the only materialist out there, and in a sense I agree with him. A lot of people who call themselves materialists end up being spiritualists. They start using concepts as physical objects because they never went through kindergarten physics. But there you have it. Something, that which has shape. And so, you can't do physics without an object. And that is the golden principle of physics. You can't do physics without an object. Because if you do physics without an object, like they used to do in the past, like spirits, and so on, well, you're doing black magic. You're doing action at a distance. You're saying there's no mediator out there, but things happen from a distance. And that is very scary. It's called, again, black magic or witchcraft. Okay? Okay, so let's move on to the subject matter of today. Sorry it took so long, but there were a lot of issues that I needed to cover. Okay? Let me go with this here. Space-time. Well, where do we start with space-time? What is space-time? We want to know what space-time is. If they're going to bend it and do all kinds of good things with it and explain gravity with space-time, we might as well know what space-time is, okay? And here, let's start very slowly, okay? We have here a set of number lines, which the mathematicians call dimensions or coordinates or something along those lines. No, they're number lines. And one of those is the number line known as time, which is not a dimension. It's not a structural dimension like length, width, and height. Okay, time is a number line, just number line. That's all it is. And time has no direction, but they always put a direction, as you can see there. They draw them as straight lines. Okay, and they put all these numbers in there. You know, all these number lines because they want to calculate stuff or show where they're at or things along those lines, right? And so they label these number lines, and here we build the matrix, okay? And this is what they're going to be bending. So I just want to go slowly so you see how we built this, because they always put this fishnet and you don't know where the fishnet came from. A lot of people don't know where it came from. And so I just want to show that, yeah, what you're staring at is really a bunch of numbers, and what is fake is the fishnet. You know, time is not a fishnet, neither is space. But they put a fishnet representing space-time, and what they're really talking about is a bunch of number lines, right? And then they get rid of the numbers, and what they do next is, guess what? They're going to bend this stuff. Okay, here it is. They bend it. Okay, and so that's the fishnet that you see in relativity. Okay, and so the question is this valid what they do? You know, because then they're going to put something on there like a star or whatever, and then you see the star rolling around space-time. And the question is this a valid thing? You know, here they build it little by little, right? They build this matrix. They get rid of the numbers. They just leave the canvas, you know, the fishnet, and then they bend it. They bend it and they say, look, we have all these number lines. That's what they are. And then they're going to roll a sun around it. Sounds neat? Sounds like a plan? Is this physics or what is this? So, you have to understand what space-time is. Space-time is just a bunch of number lines that concern the mathematicians. And you say, why do they represent it like that? Why do they turn in this physicality if it's just a mathematical abstraction? That's the question, okay? And here you see good old Brian Greene, just in case, because you might say, Bill, you invented this. No, I didn't invent this. Here you see Brian Greene, okay? He's going to roll the little ping pong ball around the bowling ball, right? And he tells you the moon is kept in orbit not because it's pulled by the Earth, right? But why? He says rather because of long curve in a space-time fabric that the Earth creates. So he puts the bowling ball there, you know, and he shows you how it's done. And the ball just keeps rolling around forever. Why? Because there's a depression in what? Space-time. All those lines that you see there, that's space-time. And what he's bending there are coordinates. Not really coordinates. What he's bending really is number line. Number lines are not coordinates. Coordinates give you location. And here they're talking about number lines, just pure number lines. And so, yeah, so this is what space-time is, okay? And so the question is, does that make any sense? Can you say that gravity is the bending of space-time if space-time is number lines and they're bending number lines? What sense does that all make? And so then you have all these people out there, and they say, Bill, you're taking an analogy too literally. And there they made this cartoon. Understanding gravity, space-time is like a rubber sheet. Massive objects distort the sheet, and wait, they distort it because they're pulled down by what? And the teacher says, oh my God, says spacetime is like this set of equations for which any analogy must be an approximation. And the student says, boring, I don't know. No, that was the wrong word. You should have said irrational. That's what you should have said. What these people are saying is irrational. And so what's the issue here? The issue is that these people, mathematicians, right, they say you're not supposed to take the analogy literally. You're not supposed to take the explanation, the mechanism that they're proposing literally. They're saying that they have these equations, these measurements out there, right? And they cannot present it in a language that peasants out there, like all you peasants out there, you would not understand our math. So we have to somehow translate it, like translating, I don't know, the Klingon language to Spanish or whatever. It's very difficult. And so they say you can't really translate mathematics into ordinary speech. And so you can't take the analogy or the explanation or the mechanism too literally. That's their answer to this. And so the question is, why did they even try? If they cannot offer a mechanism, a rational mechanism, what is this nonsense of turning number lines, which they call coordinates or dimensions, turning them, because I'll even accept coordinates and dimensions, but they're bending coordinates and dimensions. What does that mean? So they're bending these number lines, and they're saying gravity is the bending of number lines. But don't take the analogy too literally. Don't take what I just said too literally. Don't take the explanation, the mechanism too literally. Then what am I supposed to conclude? And so they say, well, we're still investigating. We still don't know. But then, they talk everywhere as if they knew. They've already proven everything. And so we have all these contradictions out there where they've proven everything, they know everything, but then you say, well, that doesn't sound rational. Yeah, because we cannot convert our number lines into ordinary speech, and so this is the best way that we can do it for you peasants out there. But in our world, we talk math, we talk number line, we understand each other. But we can't talk to you because you know no math. And so I just want to know why this spoon falls to the floor. That's all I want to know. And they say, well, it's the bending of number lines. And when you call their bluff, and they say, well, you're not supposed to take the analogy too literally. What does that all mean? What is this? So are we ever going to get an explanation? And here you'll have some answers from some of the great minds of mathematical physics. And these are some of the contradictions that they have out there, okay? All the irrational explanations that we ended up with. You have the self-creation of space and time. It's called Big Bang. Invisible massive black hole warps space-time. Invisible massive dark matter particles. Those are the ones that create the galaxy rotation problem or solve it. Invisible medium dark energy. Invisible tunnels to other universes, wormholes. Earth drags time around, proved by gravity probe B. Gravity warps time. You have a concept warping another concept. They have all these irrational explanations. And you say, well, does this make any sense? I mean, they don't have a single explanation for any phenomenon out there. And you say, how can this possibly be after so many, first of all, thousands of years of these people doing research, 400 years at least since the days of the scientific revolution, 100 years since quantum and relativity, a few or less for string theory, and still we have no explanation for any phenomenon. They don't know what magnetism is, they don't know what electricity is, they don't know what gravity is, they don't know what light is. And so where do we stand? And they say they've proven everything, they know everything. You can't publish a paper that contradicts relativity, string theory, or quantum mechanics. And I'm not talking about math, I'm talking about mechanisms. And they won't allow you to publish a mechanism. You have to put math for them to understand it, I guess. So the ones who don't understand are them. Normal people understand simple things. You say, how does a spoon fall to the floor? And I can explain it very easily. I'm going to do it with a pen. I hope you forgive me. Okay, here you have a pen. Okay, and I've attached something to it. It's called a rubber band, right? And I want to show you how I can make it fall to the ground because it's attached to my finger. So I let go of the pen and it falls down. Always falls down, never falls up. And if I want it to fall up, no problem. I can also do it this way in reverse. I can do gravity in reverse. Bling, see? So it goes up. Yeah. So I can do it either way because I have a physical mediator that everybody can understand. Okay, so I don't need any math. I just showed you a mechanism of how a pen can fall to the ground if every atom of the pen is attached to every atom on Earth. Do you believe it? Well, we don't care. We don't care if you believe. We just want you to understand it. Understand the mechanism we're proposing. And what these people are saying, we have no mechanism. Our mechanism is warped number lines. What do you mean warped number line? What is that? Are they strings? Are they canvas? Are they a fishnet? What are you talking about? And they say, well, you're not supposed to take the analogy too literally. That's the answer. And we don't do that anyways. That's philosophy. That's on the other side of campus, how the universe came to be, all that stuff, where the singularity appeared for the first time, called the Big Bang. Where it came from, did it come from God? Well, that's philosophy. We don't care about that. So these are the answers you get. And so, yeah, here you have good old Stephen Hawking. He's going to tell us a little bit about space-time. He says it's often helpful to think of the four coordinates. Calls them coordinates. And this is a mathematician, right? And he calls them coordinates. Of an event as specifying its position in a four-dimensional space called space-time. What does he say next? He says, it is impossible to imagine a four-dimensional space. What is he talking about? I mean, of course it's impossible to imagine a four-dimensional space because you're talking about number lines. And he doesn't even realize that. So he's saying he's got four number lines. He's trying to imagine what they look like. Of course he's not going to be. He cannot even imagine three number lines or two number lines. Because number lines have no direction or perpendicularity. Number lines have, you can put numbers in any direction you want. You can put the 4 before the 5 if you want, or after it. It doesn't matter. Numbers have no direction. But good old Stevie, since he was brainwashed so much with mathematics, he never picked up on that. Something very simple. Baby could have figured it out. Here you have another fellow. His name is Leonard Leo Susskind. You and I evolved in a world of 3 dimensions. We can't visualize more dimensions. I can visualize 3 dimensions in my head, but I use X, Y, and Z to describe them mathematically. Okay, so he's going to describe them mathematically. He cannot picture them. Now I go to 4 dimensions or 5 dimensions, I can't visualize them anymore. Yeah, of course, because you're talking about, not dimension, you're talking about number lines. That's one issue. But even if it's dimensions, I mean, how's he going to put a perpendicular dimension to length, width, and height? Of course he cannot picture it because no such monster exists in our universe. And I can't visualize them anymore. I can't say, now close your eyes and view in your head 5 dimensions because I can't do it either. So we're stuck needing what? Mathematics, because evolution didn't equip us to be able to visualize quantum mechanics. It didn't equip us to visualize 11-dimensional space-times. Evolution did this to us. These are the answers. This guy teaches at Stanford, and this is the ridiculous thing that he says. And just in case, we have their, I guess their guru came first before any of them. This is good old Heisenberg. What does Heisey say? He says, the most important step was not to see that our language is not sufficient to describe the situation. Okay? And in such a world as the path of the electron, they are quite understandable in the ordinary realm of physics when you have to do with stones or with gas and so. But they are not really understandable when we have to do with electrons. At the same time, we know that these words, which are used for describing the experiment, that they have only limited range applicability. That these words, for instance, when applied to electrons, really don't mean much. In other words, all these people, they cannot put into words their math. Because, yeah, math has nothing to do with physics, which is what people want to know. People want to have a rational explanation of why the spoon falls to the floor. Or why the pencil falls to the floor. I give them a rational explanation. It's tied and it falls. See, there it is. Look, I'm holding it down here, okay, and there it goes. Bing. Goes down. Goes up also. Bing. I can show you how the pen falls because I'm showing you a physical mechanism. But of course, if if I remove this, why would it fall? If there's nothing here, absolutely nothing, then why would it fall downwards? And push, you can't do it with particles. We've already covered that. So yeah, you have to do it through pull, and gravity is a pull force. And the only thing you had to do all these 10,000 years is identify the mediators, the physical mediators that we cannot see or touch. And hopefully, so that means we can't go to the lab or to the field and try to prove gravity or detect the mediator of gravity because it's invisible and intangible. So only an idiot would go out there and try to prove or detect what is invisible and intangible. No, this is something where you put your feet on the desk, drink a beer, and visualize how Mother Nature could be doing gravity. And hopefully you reach the same conclusion as I did, that everything has to be attached to everything else for there to be attraction. Otherwise, you cannot produce pull if you don't have some kind of elongated object between two atoms. Okay, and so that's where we stand today. Anyways, what do we have today? Well, we have all irrational explanations. Here it is one more time. Okay, you have all these irrational explanations coming out of quantum mechanics and relativity, and they get away with murder because they say this is all philosophy. We don't care about all this. We just do equations. And when we give you all this nonsense, it's because you poor peasants. You don't know enough math to understand an explanation given in math, which is only a description because they cannot explain anything with equations. You can only describe with math. And so they cannot give you an explanation. When they do give you an explanation, it's irrational, and they dismiss it as saying, well, don't take it literally. You're asking for something that belongs to the other side of campus, belongs to philosophers of physics, of science, of who knows what.